Okay, so let's jump into it. Well, we know what linear equations are already. First order linear ODE has the form dy dx plus let's use p of ty equals g of t. Right? And by the way, this is called the standard form. Right? So the standard form is where the coefficient of the derivative is 1. And so a linear first order ODE has that form. And chapter 2 is going to be focusing on this guy and how to solve, well, chapter 2 focuses on the first order ODE in general. Is dy dt equals some function of t and y. And this guy's the focus of chapter 2. So we're going to learn about different methods of how to solve guys that look like these. And so let's jump into it. I'd like you to try and solve this differential equation. So in last class we were looking at first order differential equations, and we learned about how to solve them using separation of variables. And now we have a problem like this, right? So it's a first order ODE, right? There's a y prime, that's the highest derivative, and it's linear in the y's, so this is a linear first order ODE. How do I solve it? If you divide by ln of x, then what? What would you do in that case? How would that help? There's no common x really. Oh. This one is inside an ln. Exponentiate. I mean, what are you trying to do? It's not separable. So if you're trying to separate it, okay, yeah. So I'll just throw out the spot. It's not separable. So if you're trying to use algebra to separate it, it's not going to work out for you.
Wow.
I'll give you a hint.
Suppose got your waist on the scrap. Like, what the hell?
It's like, oh, I'm trying to suppose we have mu is a function of t and y is a function of t. If I take the derivative of mu times y, what would be the result?
The derivative of mu into y plus the derivative of y into mu.
Right, the product rule. So I can just differentiate the y, then leave the mu, then differentiate the mu, then leave the y. So these two guys are the same. Now can you solve it?
What? No, I see it now.
You see it?
I see it now.
Yeah.
Mu is that guy.
Yeah.
Mu prime, the derivative of ln is 1 over x, right? So mu prime is that guy.
Oh, I thought that was a minus sign. That little dot between the ln x and the.
No, this is multiplication.
Yeah, oh my goodness. You could have just. Okay.
Do you think you know what to do now? Integrate what? So I have ln x y prime plus x to the minus 1 y equals e to the x. I'd like to use this idea to rewrite this guy.
D dt of ln of x times y?
Right. This whole left side is just the result of performing a product rule on ln x times y, right? So this side here is just the derivative of that function. Right? I can go from this to that because it's really just a product rule in disguise, right? It's just the right side of the product rule. And now how do you think I get to y? Now I can integrate to get rid of the derivative, right? So I can integrate both sides. This side I'll just be left with ln x times y by the fundamental theorem of calculus, and the integral of e to the x is e to the x plus c. And so we have ln x y equals e to the x plus c. This means that since my x is greater than 1, in particular it means that ln x is not 0, because ln of 1 has to be 0. And so I can divide by ln. And this is the solution. So we had this crazy looking first order differential equation. It was not separable, let me emphasize that. But because of the form that the left side was in, we could actually solve it without too much trouble. Just realize that, oh, it was just a product rule on the left side. Another example. How would I do that one? And again, it's not separable, so don't waste your time.
Same thing as
The
that.
same way.
It's basically the same thing, right? What would the left side be? That's just the derivative of that. If you do the product rule on this, you would get that. Then to undo this, I'll integrate both sides. The integral just undoes the derivative over here, which is minus 2ty equals t cubed over 3 plus c. And then I can get y would be equal to t cubed over 3 e to the 2t plus c e to the 2t. Right? So it sort of looks scary, you're not sure what to do, it's not separable, and then you sort of realize, oh, the left side is really something nice that I can take advantage of. And then you start to think, wouldn't it be nice if this always happened? Of course, it doesn't always happen, but as it turns out, it would be nice. But as it turns out, we can actually force this to happen pretty much all the time. And once the functions are nice enough for us to integrate, because we need to integrate right there, things will work out. So if you have a linear ODE, it turns out you can sort of force this thing to happen even if it's not currently happening, and then take advantage of it. And you do that by using the integrating factor method. Because what we do is we actually multiply by a function that we call the integrating factor. That's going to sort of mess with our differential equation and get it into a nice form that we can sort of do this manipulation with. So I gave it away. I told you all we have to do is multiply by some convenient function and this will happen, but how do we find such a function is the core question. Call this function mu. Right? That's what we're going to call it. And it'll be mu of x or mu of t depending on what your independent variable is. Right? So let's say we're given a differential equation that looks like, in standard form, that looks like y prime plus some function times y plus some other function equals some other function. And then what we're going to do is we're going to multiply through it. We're going to take this function mu, multiply the whole equation. What do we want to happen?
We want to be able to create a very easily integratable form.
Yes. In particular, what do we want to make the left side? You want to make it the product rule. Can you give me an equation that we could describe that would make that the product rule? What must be true for this to be the product rule?
It must have itself and the derivative and additive parts.
Okay, so what does that mean?
When you differentiate the function, it has to have the result has to be itself. So the only function that would kind of fit would be
Not necessarily, no.
Mu prime is equal to pt times u.
Right. Mu prime would have to be equal to p times mu, right? Because this has to be mu times y prime plus mu prime times y, right? That would be the product rule. So this guy, what we need is for him to be mu prime. If that's true, we can do the product rule, right? So what we need to make this work out is we need to multiply by some function that this becomes true, right? In other words, I need d mu dt to equal p times mu. How do I find such a function? How do I find mu?
Integrate.
How can I integrate? Integrate with respect to what? Well, I have a dt over here. Can't do that. It's separable. Right? Don't forget that. That's important. It's a separable differential equation. I can bring the mu's and the t's on each side, right? Remember, p is a function of t, even though I don't write it. Right? It's not a constant, it's a function. Right? So I can bring the mu on this side, and then I have p of t dt on that side. I can integrate both sides. Here I would get ln of mu. Here I would get the integral of p dt, right? Which p is an arbitrary function. I really don't know what the integral is. I'm hoping it's something nice that I can integrate, right? Plus some constant, which means that mu would be equal to e to the antiderivative of p dt, right? Sure, some c could be here. Right? So remember, this will solve this differential equation for all values of the constant c, right? So since I can pick any value, I just pick a nice one like 1, right? Obviously I could pick c equals 0, but if you multiply both sides of the equation by 0, you get 0 equals 0, you can't solve anything. And picking a constant that's not 1, pi or 3.4 is just, why give yourself a headache? Choose c equals 1, you get a nice thing. And then you end up with mu is just an exponential raised to the integral of this function. That was the coefficient of y, right? So it turns out, what we've just shown is, and everything was arbitrary here. I didn't pick particular functions. Nothing was very specific. But it turns out that if I multiply through by a function that looks like this, I will transform any first-order linear differential equation into the product rule, right? And once the functions are nice enough for me to integrate, I can solve it. Right? So this leads us to what we call the integrating factor method. Method of integrating factors. So let me emphasize here that it is not separable. Separable. Because if it's separable, you just separate it. Don't kill yourself. Multiply through mu equals e to the antiderivative of p. To get mu times y prime plus p mu times y equals g times mu. And this basically will always turn this side into the product rule. It's just going to happen. We solved for this to happen. So then what we can do is we can just integrate both sides. This implies that mu y would be equal to the integral of mu. C, which means that your y will always be let me emphasize here, these are functions of t. So any first order linear I can multiply through by this guy, and provided all the integrals are nice, this will always work out. I can always force the left side to become the product rule. This method is called the integrating factor method. And I suppose step 3 is solve for y. So let's do a few examples. The first one, take note it is not separable. Can I get rid of this? This part here. And I get rid of this. Right? So notice that these are all first order linear differential equations, but none of them are separable. So how do we solve them? Mu. So here mu is equal to e to the
Integral.
integral of 2 dt. Right? So that's just e to the 2t, right? Remember, we don't care about the plus c, anyone will work. So what I'm going to do is I'm going to take this guy, multiply through by e to the 2t. What you'll notice, this is a function times y prime plus the derivative of that function times y, right? This guy ends up being the derivative of that. Which means that this left side is just the product rule. This is just e to the 2t times y all derivative.
Why do you have negative t?
Because of the.
E to the 2t times e to the minus 13. You have to multiply both sides of the equation, right, to keep things equal. Right? Now by doing this, what happens is the left side will always be this. You don't even have to think about it. You take that mu times the y, all of it derivative, that will be the left side. And now I can integrate both sides. This guy we have to keep, this constant. This means that your y would be, now I divide by e to the 2t. And that would be our answer. First order linear ODE, not separable, but I can use the integrating factor method on it. Multiplying through by a convenient function turns the left side into something really nice that I can reverse really easily. Okay, let's move on to this one. Again, first order ODE, not separable. How do I do it?
And you consider mu and square
Mu is?
to the left,
No.
-2.
No.
X squared.
No. E to the integral of minus 2x. Right? Right? Whatever is in front of the y, it's e to the integral of that thing. This is just what? E to the minus x squared. And so now I'm going to multiply this guy through by e to the minus x squared. I don't have to think about it, the left side is going to be this guy. And now I just integrate both sides. So the size e to the minus x squared, y would be equal to, how do I integrate this guy? E substitution. And the result would be what? Right? Plus c. And then to solve for y, I just divide by e to the minus x squared. Therefore, I get y is equal to minus 1/2 plus c e to the x squared. And they gave me an initial condition, y of 0 equals 0. Here. This means if I plug in x equals 0, I get y equals 0. So 0 is equal to minus 1/2. If x equals 0, I just get c. It means that c is 1/2. This means that finally the solution is minus 1/2 plus the half e to the x squared. And that is the solution to my differential equation. Any questions? Mm-hmm.
What does ODE stand
ODE, ordinary differential equation. That was in the first lecture. Did you miss it? Or did you absent? It means ordinary differential equation. Just means we're dealing with ordinary derivatives. Later on we'll deal with partial derivatives. So it's just to signify what derivatives we're dealing with. All right, how about this one?
Divide by 2.
Divide by t. Why do we have to divide by t?
Because you want in standard form.
One in standard form, right? So don't just jump the gun and be like, oh, mu is e to the 2t. It's not going to work, right? You have to divide by t because notice that for the integrating factor method to work, you have to be in standard form. So the first thing you would do is divide by t. And so now your mu would be e to the integral of 2 over t dt, which is just e to the 2 ln t, which is just t squared. This means I multiply this equation through by t squared, right? This guy would become t squared y prime plus plus 2ty equals t sine t. Notice that here, if you saw it, you could have realized that if you multiply through by t, it would have worked, because this would have given you t squared, this would have given you 2t. But if you don't see it, don't worry about it. Put it in standard form and find your mu and then multiply. It'll save you some time. The left side is just going to be t squared y all derivative. This side would be t sine t. And then we integrate. T squared y equals, what's the antiderivative of t sine t? How do we find the antiderivative of t sine t?
We do integration of
Integration by parts. Who's the u?
sine
T would be the right? Leate. Remember calc 2? Okay. So t would be the u. That's the guy you're going to differentiate. Sine t would be the guy you're going to integrate. So this would be minus t sine t plus the integral of cosine t. Right? Cosine. Right? So it's u times v, right? Minus the integral of v times du. So that's our guy, and so this would be minus t cosine t plus sine t plus c. And so our y would be, I would divide by t squared. So I would get minus cosine t over t. I'm going to rewrite it over there. Plus sine t over t plus c over t. I need to find the constant because they gave me an initial condition. So you know that y of pi over 2 is equal to 1. This means that when y is 1, t is pi over 2. Cosine pi over 2 over pi over 2 plus sine pi over 2 over pi over 2.
Square, right?
This should be a square. Pi over 2 squared plus, this is also t squared, c over pi over 2 squared. Right? That okay? And so now, what's cosine of pi over 2?
0.
0. What's sine of pi over 2?
1.
And so now I can solve for my c. Multiply by pi squared over 4. 4 would be 1 plus c. This means that c is equal to pi squared over 4 minus 1. This means that my y would be minus cosine t over t plus sine t over t squared plus pi squared minus 4 minus 1 over t squared. And that is the solution. Down the last guy. So again, we had this differential equation, not separable, so we're thinking maybe integrating factor method can work because it's linear. It makes sense to assume that. First step is to put it in standard form. That is very important. The method won't work unless it's in standard form. Then you're going to find your integrating factor, which is always going to be e to the integral of whatever guy is in front of the y. Right? Then, once you multiply through by that, the left side is just going to be the integrating factor times y, all derivative, and the other side is just going to be the function times the mean. And then you integrate and solve for y, basically. Right? This is the integrating factor method. Let's try it on this one. Alright, how do we do it?
So we multiply the whole thing by x.
Right, need the coefficient here to be 1, so I'm going to multiply through by x.
Then if we integrate negative 2 over x, we're going to get ln of. Well, yeah, we can. Right, so it would be then ln of 2 ln of x.
Negative
2 ln of x.
2.
Where would that go?
So that would be for the integrating factor.
Nope, that's not the integrating factor. What's the integrating factor?
E.
There's an exponential in there. E to the integral of that. Which is e to the minus 2 ln x, which is just x to the minus 2. Which means I can multiply through by x to the minus 2. X to the minus 2 just gives me cosine here. And so this side would be x to the minus 2 times y all prime cosine x. And that one's not so bad. You integrate both sides. This will give you x to the minus 2, y equals integral of cosine sine. And so y would be x squared sine x. X squared. That would be the general solution. Right. E to the integral of that. Right? Don't forget that. It's pretty important. Do you have it? So you have a linear first order. If it's not separable, what you do is put it in standard form, multiply through by e to the integral of the coefficient of y. That will transform the left side into the product rule, and you undo it by integrating. This is called the integrating factor method. And it's just another technique of, finding the solution to first order linear differential equations.
Actually does it for
2.1. it made sense for me to talk about separable equations when doing the introduction, so we already did separable. But there's another thing in this section that we need to know, and it's called homogeneous differential equations. I put homogeneous in quotes because to me it's sort of a misnomer, because it's going to mean one thing here that for the rest of the book it's going to mean something completely different. So I don't know why they call it homogeneous. It's just, I keep calling it that because of tradition, I guess, but it's, so, suppose is homogeneous. So let's say I can somehow have a function that I can write as a function of purely y over x. So let me give you an example. I have dy dx equals, and we're going to solve this one in a bit. I think we'll only get through one example at this point, but we'll finish up next time. So this is an example of such a function. Note we can divide through by x, of course assuming it's non-zero, to get, if I divide this, the top by x, and divide the bottom by x, right, so it's sort of like multiplying by 1, I can get dy dx would be equal to y over x minus 4 over 1 minus y over x. Right, so you see I can sort of write it as a function where the variable is just y over x, in particular y over x, right? Now whenever that happens, I call it homogeneous. Because there are no x's or y's hanging out by themselves. The only variables that appear are in the form y over x. I can't always do this, but sometimes I can. It turns out we can force these to be separable. Why do we want to force it to be separable? For one thing, I want you to appreciate that this is not linear, right? Which means the integrating factor method that I just taught you wouldn't work. It's also not separable in its current form. So I couldn't just separate it by what I taught you the class before. So this is a whole new kind of thing, right? But it turns out whenever I can do this particular maneuver, it turns out I can force it to be separable somehow. No, I'm not going to multiply by an integrating factor, but I'm sort of going to do a substitution and change things up. Substitute v equals y over x, right? Call this a variable. Right? In particular, this means that y is equal to v times x. Note v is a function of x. it's not a constant, it's a variable, it's a function of x. I should be using t. Bad habits. T or x, we use them interchangeably sometimes. So now what I can do is I can actually differentiate this line. Right? dy dx would become what? If I differentiate this. Differentiate x, leave the v, plus you leave the v, you leave the x, and differentiate the v. Substituting these will make equation 1 separable, as it turns out. So, I mean, once you get the idea, I don't particularly like the idea of, sort of algebraically going through something and figuring out if you can write it as this and then doing this. So we sort of have mechanical steps that you can mindlessly follow after you get this to sort of do it. Mechanically follow steps. So, given dy dx equals f of xy, where it is not separable, right, so this is just giving you another situation that we have to deal with sometimes. Check the following. If you change each x to a constant times x and you change each y to a constant times y, it should make no difference whatsoever. And if that happens, it turns out it's homogeneous. You will be able to write it as a variable of y over x. Right? So, for example, if I had y minus 4x over, if I take f of xy, let me write that down first. If this is true, it is a homogeneous ODE. And so for example, if I let f of xy were this function, then if I take f of kx, ky, what would that be? I would change all y's to ky's, change all x's to kx's. What would you be able to do? You'd be able to factor out a k from the top, right? And also factor out a k from the bottom. The k's would cancel, and you'd get the original function back. Right? Turns out this is homogeneous. I could do this if I were, if I wanted to follow through on the algebra, right? All I have to do is check this. If this checks out, it turns out you could do this, so you don't have to check that in specific, right? So it's just an easy way to check that. If homogeneous, take these steps. 1. replace f of x, y with f of 1, v. This would be equivalent to taking all the y over x's and putting in v's, and then 2 replace dy dx with b plus x dv dx, right, which we derived there. 3 It would be separable in terms of v, solve it for v, then you can replace the v with y over x and then find y. Right? Can I get through that example? Let's do it. Let's actually do this guy. Check. F of x, y equals f of kx, ky. So I know it's homogeneous. I actually did the working to do the check over here, so we know it's homogeneous. This gives us, replace this guy with that. Over here, everywhere you see an x, replace it with 1. Everywhere you see a y, replace it with v. Everywhere you see x, replace it with 1. Everywhere you see y, replace it with v, right? F of x, y becomes f of 1v. All x's, turn them into 1s. All y's, turn them into v's. Turns out this is separable. A warning here, this is one of the kinds of problems that really is going to test your algebra and your calc 2. The integrals are usually nasty, stuff you have to do by partial fractions or trench law, things like that. So that's why I asked you about that the first day. So let's actually go through separating this. I bring this v over. Subtract v, and I'd actually combine these. How would I combine them? That's right, algebra, common denominator. That is correct, you in the back. Right, so this is v minus 4 minus v squared all over 1 minus v. This becomes, this would be plus v squared, so this becomes v squared minus 4 over 1 minus v. Then I can divide by this to move it over here, and divide by x and multiply by dx to move that over there. I would end up with 1 minus v over v squared minus 4 is equal to dx over x. And it is then separable. I've separated the variables. I would integrate this guy and integrate that guy. Turns out that this guy, partial fractions. This guy's easy, it's just ln x plus c. It'll be ln x on that side all the time. It's just how it's going to work out. This side is the side that's going to be trouble. Usually it's going to be something nasty. It's very typical, so prepare yourselves. So now I'm going to want to do these in partial fractions. So this is v minus 2. I know this is going to be v plus 2 dv. What goes on top of here? Well, v equals 2 make this 0. So if I plug in 2 here, I get minus 1 over 4. So the top here is minus a quarter. V equals minus 2 makes that 0. So plug in minus 2 here. I again get minus 1 over 4. So this is minus 1 over 4, right? Those are the partial fractions. And so the integral is minus 1 over 4 ln v minus 2 minus 1 over 4 ln v plus 2. I can sort of multiply by minus 4. Is that true? This, I plugged in something probably in here, minus 2. That's actually 3 over 4. Which would make this cube. All right. So this means I have ln of v minus 2 times v plus 2 all cubed equals, I can write this as ln of our constant times x to the minus 4. And so now I can drop the ln's. V minus 2, v plus 2 cubed equals some constant x to the minus 4. And so x to the 4th times v minus 2, v plus 2 cubed equals some constant. And that's pretty much as nice as I'm going to get it. Now I can swap out the v's for y over x's. And I can take one of the x, multiply into here. I would get y minus 2x. Take the other x cubed, multiply into here because that's cubed, and I would get y plus 2x cubed equals a constant. It's also typical. I stole this from one of the even problems in the book, and that's how they had the solution in the back. So I decided to bring it to the same form. Yeah. So the idea is this: you have another first-order differential equation. Then you're like, oh yeah, try separable. It's not separable. You're like, okay, integrative factor. It's not linear. So are you dead in the water? Do we give up? No, we don't. Last ditch effort to win the fight, we check this. And they're like, it checks out, yes. Replace this guy with that. Replace all y's with v's. Replace all x's with 1. This will be separable. You have to remember your algebra so that you can get to this point. Then you have to remember Calc 2, say that you can integrate the guy over here. Very usually, it will be a very horrible guy to integrate. Right? Then once you integrate both sides, you go through and you try to get things as neat as possible, and then you can sub out the v's for the y over x by back substituting, and then you can write the answer in y over x. Don't worry if you can't solve for y, because you can't solve for y in this case. And it's usually typical to have implicit solutions. So the solutions here can be ugly, and the integrations can be ugly, but this method would be the way to do it. And we'll actually cover a couple more examples next time. So for that, now we'll stop.
Yeah, we'll stop. My bad. Well, almost. I didn't see that.